connecting your world.
All right, let's dive right in. The internet feels like this incredibly solid, permanent thing, but the entire global map that makes it work is drawn by a protocol called BGP. And the thing is, it's all built on trust, and that trust is, well, surprisingly fragile. Today, we're going to break down how we protect the very heart of internet routing.
And yeah, let's not pull any punches here. This warning from an early internet engineering draft gets straight to the point. Without the right protections, the system that directs pretty much all of our data traffic can be tricked, it can be disrupted, or it can even be torn down by someone sitting halfway across the world.
And take a look at this. This diagram really shows you just how vulnerable one single connection can be. What you're seeing is called an attack tree, and it shows that a bad actor has a whole menu of options, from faking a reset message to compromising a router to do the same thing, knock a BGP session offline and cause a serious outage.
So, what is this BGP thing anyway? The best way to think about it is like a global postal service, or maybe a GPS for the entire internet. It works between these huge independent networks, we call them autonomous systems, and it's constantly telling them the best, most efficient paths to send your data to literally any destination on the planet. Simple as that. No BGP, no internet. Okay, so here's the problem. BGP was designed way back in a much more trusting era of the internet. It just runs on a standard connection, TCP port 179, and it has absolutely no built-in way to prove who it's talking to. And this isn't just some theory. This exact weakness is what allowed a telecom company in Pakistan to accidentally hijack all of YouTube's traffic back in 2008, just by announcing the wrong routes.
So, to fight back against these kinds of attacks, network engineers came up with a first line of defense. You can think of it as a kind of cryptographic secret handshake that's been the go-to standard for decades.
And that handshake is called TCP MD5 authentication. It's an old standard, RFC 2385, and its job is to make sure that every single piece of data swapped between two BGP routers is signed with a secret password. This proves it came from your trusted neighbor and not some imposter.
The way it works is actually pretty straightforward. You configure the exact same password on both routers. The sender then creates a unique signature, a hash, using the data in the packet plus that secret password. The router on the other end does the exact same math. If the signatures match up, the packet's legit. If they don't, it gets dropped immediately.
But, and this is a big but, here's the catch. While MD5 is basically everywhere, it's supported by just about every router out there, it's got two huge problems. First, the MD5 algorithm itself is now considered cryptographically broken. And second, and this is a huge operational headache, if you want to change that password for security, you have to tear down the entire BGP connection. That means an outage, every single time. Okay, so MD5 is old and it's clunky. To fix those flaws, the engineering community went back to the drawing board and designed a successor from the ground up. One built for much stronger security and, maybe even more importantly, for operational stability. And that's where TCP-AO, the TCP authentication option, comes in. This is the official modern replacement for MD5. Not only does it use much stronger crypto, but it was specifically designed from day one to handle the needs of these super important long-lived connections that BGP sessions are.
And this right here, this is the absolute game changer. It's called hitless key rollover. For the critical infrastructure that runs the internet, this is huge. It means you can add a new password, switch over to it, and then get rid of the old one, all while the BGP session stays up and running. No more scheduling late-night maintenance windows just to do basic security hygiene.
And the benefits don't stop there. TCP-AO brings a whole suite of upgrades. It supports modern, much stronger hashing algorithms. It lets you have multiple keys ready to go for a single session, which makes those transitions totally seamless. The whole security process is just more robust, and the system is truly built for the kind of always-on connections that power the internet.
So when you put them side by side like this, the difference is just stark. It's not even a fair fight. TCP-AO is better in every single way. Stronger crypto, non-disruptive key changes, and a way higher level of security. And yeah, a lot of networks are still using MD5 because of old hardware. But for any new connection you're building today, TCP-AO is the clear winner.
Okay, so authentication is great, right? We've verified our direct neighbor. We know the router on the other end of the cable is who they say they are. But what about an attacker who isn't trying to impersonate your neighbor, but is just flooding your router with junk from thousands of miles away?
And that brings up a really critical question. An attacker doesn't need to be next door to cause chaos. They can be anywhere on the internet, sending a fire hose of spoofed packets right at your router's BGP port, hoping to overwhelm it or maybe trigger some kind of bug. How do you stop that?
Well, enter the Generalized TDL Security Mechanism, or GTSM. Now, this isn't authentication. There are no passwords involved. It's more of a simple but really clever sanity check. Think of it like a bouncer at a club who only lets in people with a local ID.
So here's the trick. Every time a data packet crosses a router, a little number inside it called the time to live, or TTL, gets reduced by 1. Your router sends its BGP packets out with a TTL set to the maximum, 255. So logically, a packet from your direct neighbor is the only one that could possibly arrive with that same value of 255. GTSM just enforces that rule. Any BGP packet that shows up with a lower TTL had to have come from farther away, and so it gets instantly thrown in the trash. So what's the big picture here? The truth is, there's no single silver bullet for this stuff. Really securing BGP isn't about picking just one tool. It's about building layers of defense to create a routing system that's both resilient and trustworthy.
The real best practice, then, is to build these layers. You use TCP/AO to make sure your direct peers are legit, and you use GTSM as a sort of perimeter wall to block those remote attacks. You combine that with basic firewall rules, and suddenly you have a really robust defense. A big part of the goal is to create this chain of trust by working with your partners to get them to adopt these modern standards too, while of course always keeping an eye on your own network for threats.
And all of this leaves us with one final and pretty pressing thought. We are building these unbelievably complex, absolutely critical systems on top of protocols that were designed in the 80s and 90s. And as we develop and roll out new tools like TCP/AO, you have to ask yourself, is the pace of our defense evolving fast enough to keep up with the threats that are targeting the very foundation of our connected world?